Pente is a zero-sum simple two-player strategy game. It is fully observable, deterministic, episodic, static, discrete, and known. It is played with black and white stones on a 19 by 19 board. The object of the game is to get 5 stones in a row before the other player. To create an AI player for this game, I first implemented a depth-limited minimax algorithm. A minimax algorithm will look ahead at all possible moves for the player and all the possible reactant moves that the opponent could take, and returns the most advantageous move for the AI player. This repeats to varying plies. One ply is one move for each player. The number of plies deep the algorithm looks is specified by the depth ahead of time. The time the minimax algorithm takes to calculate a move grows exponentially with the depth. This means that after just a few moves, it can take quite a while for the minimax algorithm to calculate the next move. In order to improve the time that the minimax algorithm takes, I added an alpha-beta pruning to it. The alpha-beta pruning removes obviously bad branches from the search tree. Alpha-beta is able to remove these branches by knowing that the opponent will pick the worst play it can in a given branch. Using this technique, we can significantly speed up the time that minimax will take. The minimax algorithm depends on an evaluation function. I scored the game at first by using the number of pieces on the board and the number of pieces in a row. So the number of 1s, the numbers of 2s in a row, 3s in a row, and 4s in a row. Next, to try and allow my AI to learn what the weights may be, I implemented simple linear regression. To get the data for simple linear regression, I generated random gameplay. I represented black winning with a 1 and white winning with a 0. Linear regression is able to plot a line through many dimensions, but since it is only a line, it may not be able to learn the weights very accurately. To find the best fitting line through the data, the computer uses least squared estimates. This means that the line that is chosen is the one with the minimum total squared values of the distance between the line and the data points. Since there is only one minimum value for the least squared estimate, it is simple for the computer to find what this line will be. When they only have binary data, a line is not the best way to fit the data. Since the response variables are only 0s and 1s, the best function to use would be a logistic one. A logistic function is bounded between 0 and 1, and would be better able to predict the intermediate values. Pi represents the estimated probability. We can solve for eta and then use a link function to solve for pi. This estimate for finding the value of the game state was much better than the simple linear regression. The first run at using the logistic equation to solve for intermediate game scores wasn't as successful as I was hoping for. When I looked at the statistical results, I noticed that the p-values of the variable counting the number of stones on the board was very insignificant. After this was removed from the model, it was better able to perform. Using the logistic equation and a depth of 2, the AI was able to play strategically.